So far in the course, we have looked at a number of circuits, both combinational circuits as well as sequential circuits. Now, those circuits are in varying degrees of complexity. We have seen circuits which are very simple, which have only just 2 or 3 gates. We've also seen multiplexers which are made of more number of gates, decoders with even more number of gates at times. Then we have seen latches, flip-flops, where it seems that the number of gates do tend to increase as you try to achieve more and more. But from a bird's eye view of this course, the level of complexity that we have seen is hardly a fraction of what actually goes on in the real world. The complexity that we all have encountered in the course so far, in whatever amount of lectures has been covered, that complexity is just a fraction of what is actually there in today's world outside. So anyway, that is beyond the scope of the course. In case any of you happen to take more advanced courses in digital systems, you will get a flavor of what complexity looks like in the real world. So there are examples of really complex systems such as processors. You have microcontrollers. You have many real-time digital systems such as traffic light controllers and many complex display systems and so on and so forth, where the amount of logic that is required to design number of gates or number of transistors is very high. So in that case, supposing somebody gives you the task of designing a very highly complex system, then how would you go about it? So in such cases, if you have, let us say, a system which has 20 inputs and 30 outputs, you can hardly now sit down and write a truth table with 20 inputs. You will end up having 2:20 rows, which is almost a million. So that is ridiculous. You cannot hope to write a truth table for something that is as complex. We have the maximum number of inputs we have dealt with is 4. We don't even know what will happen if there are 5 inputs. How will the K-maps look like? So the point is, as and when the complexity increases in the system or in the requirements, then and then even the job of digital designers like us, that also becomes more and more challenging. So obviously, now there are 2 parts to it. First is the design part. Suppose I do manage to handle the complexity and somehow come up with a system. I take pains to actually solve K-maps, write truth tables, and sort of reach the solution no matter how many pages I have to write or how many days or weeks I have to spend. Irrespective of that, I come up with a solution. The next part is that whether the solution, the circuit that I have designed, whether it will actually work or not. There is no real way to verify. Once we have a small system, we can write a small truth table, we can solve using a K-map, and then we can get an expression or a circuit which is supposed to be the minimized form of that function. And once we have that circuit diagram, we can actually very quickly test it out for some cases and say that okay, they seem to work, or if they don't work, maybe I have made some mistake. But even that thing becomes very, very challenging as the complexity of the system increases. So there are two things. The thing is, how do we design complex systems? So by hand or manually becomes very, very difficult. This second part is that supposing we even manage to accomplish the uphill task of designing the circuit. Suppose we solve the problem and come up with a complex circuit. How do we know it is correct? How do we know that it's correct? So these are the two questions every serious digital designer has to ask at some point of time. So definitely, as point number 1 mentions, manually solving things become difficult. And same for point number 2, manually testing, that is also not so easy. Testing whether that circuit actually works with hand, that kind of calculations could also take days or weeks. So therefore, we take the help of tools. We take the help of tools which are called as computer aided design tools or CAD. So there are these simulators where you can define gates, you can define flip-flops, you can define multiplexers, so on and so forth. But sometimes the system may be so complex that just by looking at the specifications of the system, it may be impossible for you to say how many gates or how many multiplexers, how many decoders, how many flip-flops you're going to need. It's impossible. So the computer aided tools that we use should not just give us a way to show the interconnections of different logic elements such as gates to realize a circuit, but it should also provide a means through which we can describe the behavior of the circuit without having to actually tell these many gates, these many muxes, these many flip-flops. So what do we want from our computer aided design tools? Should give us the provision to define circuits using connections of known logic elements. Logic elements can be gates, multiplexers, so on and so forth. The second point is should also give the option of defining the circuit without having explicit knowledge of the logic elements required. The logic elements required. So what happened was that ever since the time people began to get very serious about digital design, people have also been researching different ways through which we can do computer aided design. And so the question came is that, can we describe a circuit in the form of a program? Can we describe a circuit in the form of a program, either using gates or using some other means? But since people, and particularly I'm talking about the period of, let us say, the 1980s, when technology was slowly booming, researchers began to ask that, can we, before we actually, waste a lot of money and time building a circuit from scratch, which we don't even know will work, can we first write some kind of a simulation program where we can use any known programming language to define circuits? Well, at that time, people knew of languages like C, BASIC, Fortran, COBOL, Ada, so on and so forth. So people began to work with these languages and see whether those languages can be used in composing programs or codes to define circuits. But one thing then people realized is that while it is one thing to write a program using any programming language for some kind of software application, it is an entirely different thing to write a program for a circuit. Now, can you guess why that is? Can you guess why that is? Why is it more challenging to write a program for a circuit? Well, normally, let us say if I write a C program, I write something like this. So I write a main function where, let us say, I declare some variables, let us say int x, y and z, and then I define something like x equals y plus z, and then let's say I define again something like y equals x minus z, and so on and so forth. This is the example of a C program. So the thing is, while executing this program, it gets executed line by line. First this gets executed, then this gets executed, and then this gets executed. But remember, a circuit is not like that. Suppose I have a logic circuit which looks like this. This looks like a very simple circuit. But from an electrical point of view, this gate and this gate, they are working all the time. It does not matter whether the inputs are changing or not. The outputs have to be always there and the gates have to always work. So a program, it executes line by line. So this is called as a sequential execution. Whereas circuit elements are always there. They're always working. So circuit elements are essentially opposite of sequential. They are called as concurrent. Concurrent means blocks which are working all at the same time. In a programming language, never will you see that all the lines are being executed at the same time. That's very, very rare. But in case of logic elements, all of them in a circuit work at the same time. So you can hardly say that, okay, I will wait for this gate to work, then this gate to work, and then this gate to work. No, it doesn't work like that. Okay, so therefore, you cannot use known programming languages to define circuits. Therefore, use of known programming languages for defining circuits is difficult. Okay, so that's what it is. So that's what it is. So therefore, in the 1980s, many people started working to develop languages that are suited towards circuit design, languages with which we can define circuits. So in the year 1987, one language was developed by the United States Department of Defense. They developed this language which was called as Vhdl. And in 1992, there was a company called as Gateway Automation. They developed one language called as Verilog. They developed a language called as Verilog. So these two languages, they look like programming languages, but they are not programming languages. So therefore, let me mark them. These look like programming languages, but they are not. So the question is, if they are not programming languages, what exactly are they? They are called as HDLs, that is hardware description languages. Hardware description languages. Okay, this is how these languages came into existence. However, the designers of these languages realized that, anyway, the public has to, or not the public, the engineers and researchers anyway have to deal with a number of programming languages. So it would be little challenging. It would be little challenging if we introduced languages which are totally new. So therefore, while these languages are not exactly programming languages, they are hardware description languages, their syntax is essentially based on some known language. So for VHDL, the syntax is based on a programming language called as Ada. The syntax is based on Ada. Ada is a very old programming language. Now it's not very much used, although the name Ada was given after Lady Ada Lovelace, one of the early pioneers of computers. And Verilog is the language whose syntax is based on C. And C is still used in many places. And C is something that many of us do learn at an introductory level. So since C is something that is known to us, we will choose the language Verilog to study a little bit more further. Now, Verilog looks like C, the syntax. Now, let me give you a very simple example of how to use Verilog. So the first thing about Verilog is that any circuit or system that you define is called as a module. So let us say I want to describe a full adder in Verilog. So let me call this as full adder. And as we know, a full adder has 3 inputs and 2 outputs. Let me call this as A, B and C in, and the outputs as sum and C out. So therefore, the first line that you write in any Verilog code, now we are not going to call these as programs. We are going to call them as codes or descriptions. In a Verilog description, the very first line that you write is the module description. That is module, let me call this as full adder. Now this full adder, in place of this word, you can have the name of any module or the circuit or the system that you are designing. And then in brackets, just like a function, you are going to write down the pins of the system, that is the inputs and the outputs. So a good convention is to write the outputs first. Let's call this as C out, sum, A, B and C in. Then every line ends with a semicolon. So although there is no hard and fast rule, you can write the names of these inputs and outputs in any order that you want. It is always a good practice to write the outputs first. The reason is that in the inbuilt gates in Verilog, the outputs are always written first. Okay, so we shall see that shortly. Now we can describe this full adder using the gates that you already know. So let us say I can describe it in this way. I can say that A, B and C in, I can combine them by means of an XOR gate and get sum. And then I can have 3 AND gates, AB, BC in and then C in A. And these are all combined by one OR gate to realize the C out function. So let us say I want to define it in this way. The first thing that you need to do in case of any defining circuit is you need to first define which is the input and output. So we will write output C out, comma, sum. Just like how you declare variables in a C program. And then I will say input A, B and C in. So the words module, output, input, these are all keywords in Verilog. Okay, so you can write single line comments like this. I can say defining or declaring input signals. You can also write comments like this in an asterisk. I will say declaring output signals and then end the comment this way. So just like see, this is a multi-line comment, this is a single line comment. Now whenever you define gates, it's always good to give them some kind of a name. Let's call this as x1, let's call this as a1, a2 and a3 for the 3 AND gates, and let's call this as o1. These are called as instance names. So when I'm declaring an XOR gate, then I will say XOR. XOR is again a keyword. And then I'll say XOR X1. Now this is like a module. XOR is like a module which is already there in Verilog. I just have to call it like a function call. So over here, an XOR gate has one output, but it can have n number of inputs, of which n is at least 2. So therefore, since the makers did not know how many gates or how many inputs would be required for a gate, they thought it is better that we write the output first. So here the output is sum. So for all the inbuilt gates, the output has to be written first. That is why it's a good practice to write the outputs first while defining the module, in case you use this module for some other application, which is very much like it. So then XOR X1. The output is sum. What are the inputs? A, B and C. This is the first instantiation of the XOR gate X1. Then I will write for the AND gates. I will say AND A1 for A1. What I'm seeing is that there are these three outputs. There are these three outputs. So let's call these as some intermediate signals like W1, W2 and W3. So these also have to be declared. We will call them as wires. Wire W1, W2, W3. So intermediate signals can be called as wires. Even wire is a keyword. So I'll say AND A1. The output is W1 and the inputs are A and B. Then I have AND A2. Output is W2, input is B and C. Then AND A3, input is W3, sorry, output is W3 and inputs are Cin and A. Finally, we have the OR gate. We'll say OR O1. The output is Cout and the inputs are W1, W2 and W3. That's it. Our circuit definition is complete. And you can now end this description with this keyword called as end module, which is a single word. You start your code with the module, you start your description with the module, and you end it with end module. It has no semicolon. So this is an example of how you can write a Verilog description for a full adder. Now, with this brief discussion, we saw how to address point number 1 in our discussion of complexity. So now we realize that we have these computer-aided design tools which can help us. Now let's come to point number 2. What about the testing? Once we have a circuit, how do we know it works? How do we know before actually doing an experiment? Can we know through any means whether the circuit will actually work on in the lab? The actual circuit, not just a simulated one. Now, once we design a circuit, the next step is to actually fabricate it. You send it to a fabrication facility. You send it to a fabrication foundry where they will essentially convert your circuit into transistors and then realize those transistors and interconnect them on a piece of silicon. But that is a very expensive process if you are making just 1 or 2 of those chips for testing. And once the chip comes back to you and you test it and you see that your design is totally wrong. Even though your Vhdl code, your Verilog code was giving you the correct simulations, but that's not enough. And that's not enough. You need to have some assurances that yes, it is going to work on the hardware also. So therefore, the question is there any way to test the design actually on hardware before making the chip? Yes, and those devices are called as programmable logic devices. Or PLDs. They are called as PLDs. These are kind of generic chips having a number of gates which can implement any circuit of your choice. Now that sounds very, very intriguing. So if I tell you I want a circuit, or I want some kind of a generic circuit that can implement any logic function, what would your first thought be? Your first thought would be of universal gates, because universal gates are NAND and NOR. They can implement any logic function that is known. Now suppose we choose AND. Sorry, we choose NAND. Now let us say I have a NAND gate. I have a NAND gate which has two inputs. Now my logic function, let us say, has two inputs A and B and has a output Y. Now all we need to do using the NAND gate is to ensure that it can do both plus operation as well as dot operation. That is the OR operation and AND operation, and also the complement. Then we will know that yes, this gate can be used to implement any kind of function. So suppose we want to first do the product. Suppose we first want to do the product. So what I will do, I can simply connect A and B to the gate as they are. Now what will I see over here? I will see A dot B, the whole bar. Then to have a product, all I need to do is connect a NOT gate over here. Then I will get A dot B. So this gives me the product. Now suppose I have this exact same gate which does not change, which again has two inputs, and my system has two inputs A and B, and it has another output Y. Now I want to realize the sum. I want to realize Y equals A plus B. How will I do that? Very simple. All I need to do is connect a NOT gate over here at the inputs, and the output is directly connected. So here this will be A bar, this will be B bar, this is A bar dot B bar, the whole bar, and using De Morgan's theorem, you get Y equals A plus B. Similarly, you can use this gate to realize a complement also. This is how we realize a complement. Now, look at the first two cases. What is happening is that in both cases, this NAND gate does not change. But in one case, we have a NOT gate at the output. The other case, we have NOT gates at the inputs. So if I keep this NAND gate as a kind of a constant, unchanging gate as it is, all I need to do is provide NOT gates at either the inputs or the outputs in a wise manner so as to realize my sum or product function. So therefore, PLDs essentially look like this. PLDs essentially have a NAND array. They have an array of NAND gates because those array of NAND gates will allow you to implement any logic function that you want to do. Then they have another array which is called as a NOT array. Both at the input as well as output. And in the middle, you have switches. Depending on whether you need to use the NOT gates or not. They have multiple switch arrays also like this. And the inputs are over here and the outputs are over here. The inputs may or may not be passed through a NOT gate. If the NOT gate is not being used, the inputs can also go directly to the NAND array. Likewise, if this NOT array is not used, this can directly go over here. So those kind of provisions are there. So these are called as switching matrices or switching matrix. So the discussion on PLDs is a little outside the scope of this course. However, there are two popular PLDs types which are being used today. One is called as a CPLD, that is a complex programmable logic device, and the second is something called as an FPGA or a field programmable gate array. So CPLDs, one of their advantages is that they can retain the connections for as long as you want them to, even when you switch off the power. But FPGAs cannot retain the connections once you switch off the power. But FPGAs are faster, CPLDs are slower. So all said and done, in this particular lecture, we took a look at the very foundational aspects of computer-aided design to solve the issue of complexity in digital systems for modern design. First, we took a look at the computer-aided design. We took a look at hardware description languages, and in particular, a very brief example of the Verilog language. These hardware description languages are not programming languages, although they look like one. Next, we took a very brief look at programmable logic devices, which can be used to implement any logic function of your choice before you actually fabricate it on silicon. These are very, very handy resources for any digital designer who is aiming to look forward to making their own circuits on silicon chip one day. Thank you very much.